back. I've got an interesting and unusual experiment to show you today, and it goes under the title of Barton's Pendulums. The equipment looks quite complicated, but in fact it's really simple. All we've got is a wooden frame here, and hanging on this side and across to this side is just a piece of string. It's a sort of washing line on a small scale. And then hanging from that, tied on, is a piece of string with quite a heavy weight on it, and then some paper cones on different length strings. So the important thing is here, we've got a heavy weight hanging off our mini washing line and a series of other objects hanging off it, all of different length. So let me show you what we do with this. The first thing to do is to take the metal weight and just to lift it up and let it oscillate. And you watch the white paper cones. And after a short period of time, it settles down and you get quite a remarkable result. That most of the paper cones don't move very much, but just one of them, here you'll notice it's the one that's second longest, seems to swing up and down much more than all the others. I'll film this from the side so you can see it rather better, but this really is going to take some explaining. Right, I'm going to start it off again and have a look at what happens to the cones as it begins. So to begin with, they all tend to move a bit, but after a few moments it settles down and you find that really only this second to longest one vibrates with a really large amplitude and the rest almost stop vibrating at all. Sure, A-level students will need to know about resonance curves and will appreciate that they're all vibrating slightly, but the one that has the same natural frequency as the frequency of the driver here will be the one that absorbs energy the best. Time for an explanation. And if you're doing A-level physics, you really do need to know about this. So I'll go into a little bit of detail, but not too much. The first thing to notice is that the weight is the thing that has the energy to start off with. We call that the driver, and it's going to oscillate up and down. It'll be shaking the string along the top, what I referred to as the washing line a bit earlier on, and shaking where these cones are attached to it. But the important thing is that if I swing the little short one, it swings up and down very rapidly. And if I swing the very long one, it swings up and down with a lower frequency. It doesn't go from side to side quite as rapidly. So each one of these lengths has a different natural frequency, a high frequency for the short one and a low frequency for the long one. So now we know that each one of the paper cones likes to swing at a different frequency. They've all got different natural frequencies. Let's start it again. And of course, this pendulum swinging, the driver with its energy, is imparting energy to the cones. But you'll notice the one that's gaining the most energy is the one that swings at the same frequency as it does. In other words, the natural frequency of this cone here is the same as the frequency of the driver. And that effect produces what we call resonance. You've seen resonance before, in fact, on the video I did with the teddy bear on the loudspeaker, where its arm began to waggle up and down at a specific frequency. And the effect you're seeing here is very similar. With resonance, what happens is that if the thing that's oscillating backwards and forwards, driving another object, has the same frequency as the natural frequency of the object that is being driven up and down, then this one will absorb energy best. The others are not very good at absorbing the energy of the oscillation because they like to oscillate at a different frequency. Resonance can be a really good thing, but there are many examples where it's a real nuisance. One of the problems you can have is with long cables, the ones that are between pylons, for example, on power lines. And if they get blown around in the wind, the mass here representing the wind, then the cable begins to hop up and down. George Stockbridge noticed this in the 1920s and invented a system rather like the one with the cone here. Because, of course, what the cone is doing is it's taking energy from what I call the washing line or the power cable, and it's oscillating In other words, it's taking kinetic energy from the cable. So he had the clever thought that if he was to tie something to the cable that had the same natural frequency as the waggling that the cable was doing, then it would steal energy from it and stop it vibrating as much. And if you know where to look, you can see these on power lines and also on suspension bridge cables and in other areas. So something for you A-level students. You will know, of course, that the frequency of the driver and the driven element are the same, but they don't oscillate together. As one goes to the left, the other appears to go to the right and vice versa. They're not actually 180 degrees out of phase, but they're pi by 2 or 90 degrees out of phase. And this is something you should learn. In other words, that when this one is at the highest point, the driven element is at its midpoint. Perhaps I'll do a video at some stage of us on large swings in a playground and make the point about where do you actually push the swing. So, Barton's pendulums. Barton, I think, was at Nottingham University when he invented this, and it's a really good experiment to show students to explain how resonance works and how the energy shifts from driver to driven element if they're tuned together or both at the same natural frequency. As a teacher, it's an absolute nightmare because if you leave this in the class for any great length of time, students will get their hands on it and probably tangle it beyond repair and you have to rebuild it again. But the frame has certainly survived the test of time. So, I hope you enjoyed that experiment, and I look forward to seeing you again next time.